In part 2 of Module 9, we will continue with our exploration of global geologic history with the Ordovician period. In this paleogeographic map of Earth during the late Ordovician, you can see the Epiric Sea encroaching onto Laurentia, also known as North America. You can also see that due to plate tectonics, Laurentia has moved further south and slightly rotated since the Cambrian. By the beginning of the Ordovician period, very little land remained above sea level in North America. This resulted in very little terrigenous clastic sedimentation and a shift to a great deal of carbonate deposition, with limestones formed from shell debris in clear, shallow water. Think back to our background lectures. What effect could this increased carbonate deposition have on the atmosphere and hydrosphere? In this photo of living stromatolites, notice the environment they live in. What can we infer about the likely environment that fossil stromatolites existed in during this time? Stromatolites help us to constrain the water depth in the rock record. They require sunlight for photosynthesis, which only penetrates into the photic zone, which is the upper 150 to 200 meters of the ocean. The widespread presence of stromatolites in Ordovician age rock is evidence of a widespread shallow Sauk Sea. The Sauk Sea began to regress during the early Ordovician, and as it did, it revealed a landscape of low relief covered predominantly with limestones. The retreat of the sea off of the craton exposed the limestones to weathering and erosion, resulting in a craton-wide unconformity that marks the boundary between the Sauk and the Tippecanoe sequences. Illustrated on the left is the position of North America relative to the equator during the Cambrian. On the right is the position relative to the equator during the earliest Ordovician. What changes do you see in sea level, and what changes do you see in the position of the continent relative to the equator? A mountain building event is called an orogeny. Orogenic events occur due to tectonic activity, usually along the mobile belts of a continent. In the case of North America, we have mobile belts on the north, south, east, and west margins. This illustration shows the major events of the early Paleozoic of North America. On the eastern margins, we have the taconic orogeny, the first orogenic event to affect the Appalachian mobile belt. Just before the beginning of the taconic orogeny, you can see when sea level dropped and the unconformity that divides the Sauk and Tippecanoe sequences begins. The taconic orogeny is named after the present-day Taconic Mountains, spanning eastern New York, central Massachusetts, and Vermont. This is the first of the orogenies to affect the Appalachian mobile belt in North America. The East Coast was a passive margin during the early Ordovician, similar to the Gulf of Mexico. This changed to an active margin in the middle Ordovician, resulting in the eventual collision with a microcontinent or volcanic arc in the late Ordovician. This block diagram illustrates the oceanic continental convergent plate boundary that developed in the middle Ordovician and led to the closing of the Iapetus Ocean and subsequently the taconic orogeny in the mid to late Devonian. The mid to late Ordovician. This graphical representation of the sedimentary sequences of North America shows that during the Ordovician and Silurian, North America was experiencing the Tippecanoe sequence. During the late Ordovician, North America was in a tropical environment. As the Sauk Sea regressed to create the boundary between the Sauk and Tippecanoe sequences, the limestone and dolostone that had been deposited in the shallow Sauk Sea began to rapidly weather and erode. As the Tippecanoe transgression started, North America experienced deposition of very clean sandstone at the base of the sequence. This is known as the St. Peter sandstone, which is so pure it is mined to make glass. Sandstone deposition was followed by widespread reefs and evaporites as sea level continued to rise. The carbonates deposited in these reef environments include corals and bryozoans, as well as other shelly fauna of the period. This illustration clearly shows the extent of sea level rise on the North American craton during the late Ordovician. What could this mean for life on Earth? During the Tippecanoe sequence, we basically had a modern reef structure and marine conditions. Most reefs were located at 30 degrees north and south of the equator. The seas were warm and shallow with little to no sediment input. In this type of environment, evaporation exceeds precipitation, so salinity tends to run somewhat higher at these latitudes. This environment was ideal for creating basins rimmed by reefs and filled in the center with evaporite deposits of salt and gypsum during the Tippecanoe sequence. A prime example of one of these basins is the Michigan Basin. This photo is an evaporite drill core. Thick evaporite sequences like this tell us much about the environment. In the case of the Michigan Basin, the evaporites are located in a basin surrounded by barrier reefs. The reefs restricted the flow of fresh seawater into the basin, where evaporation in a hot climate allowed the water to become saturated with salt and salt deposition to occur. In the Middle Silurian, you can see that the continents are still on the move, but new things are happening. Notice that the sea level seems to have decreased on the craton, and we now have activity on our mobile belts. Notice that Gondwana appears over the South Pole. Gondwana, if you will remember, is a supercontinent made up of Africa, South America, India, Australia, and Antarctica. This paleogeographic map shows the location of North America during the Silurian in relation to the equator. Note that the Michigan Basin, a restricted basin surrounded by barrier reefs and filled with evaporites, has formed, and the only parts of the craton above water are the taconic highlands and the adjacent alluvial plain. This is the end of Module 9, Part 2. In Part 3, we will begin investigation of life in the Ordovician.